Welcome to Parasitic Diseases. Today's episode is entitled Lymphatic Filariasis. It's a disease that's caused by two different parasites, but with related biologies, Wuchereria bancrofti and Brugia malayai. And together they're called the Lymphatic Filariasis. They're vector-borne, and as we'll see, they have a very interesting biology. So, where are lymphatic filariasis cases? Where do they arise? Where do they catch this disease? If you were to travel throughout the world, how would you know if you were at risk or not? Unless, of course, you had a very detailed map of where this disease is, or this infection, I should say, is actually found. What we can see here, the WHO has very kindly supplied to the world a generalized map of the regions where these two organisms, Brugia malayai, primarily in Asia and South Asia, and Wuchereria bancrofti, both in South Asia, Africa, and South America, are found. So it's not a global distribution necessarily. It's subtropical and tropical in terms of its distribution, but many, many, many millions of people, billions in fact, live within this zone of transmission, so many, many people are at risk. The history of discovery of filariasis is a storied discovery. It was very difficult not to see the presence of the disease state, which results in a condition which was dubbed elephantiasis, because in many cases the victims had swollen legs, and those legs resembled the leg of an elephant. So that's basically where this acronym came for talking about lymphatic filariasis. The discovery was actually a co-discovery. There were two independent investigators working at the same time in different places, and together, Wucherer and Bancroft discovered the microfilaria that the adult female produces during the infection, which gets into the blood and allows the vector to become infected, and the condition that it causes as an adult worm. So Bancroft was primarily a clinician. Wucherer was primarily an investigative parasitologist working in the field, and together they collaborated in the literature to name and to describe this parasite. But it was Patrick Manson working in South Asia and in China and in Taiwan, which is now Taiwan. It was up to him to actually piece together the results of Wucherer and Bancroft into a meaningful story which was verifiable by observation and discovery. And so he's credited with actually fleshing out the discovery of the life cycle of how this parasite actually carries out its life. So let's take a look at that. So Wuchereria bancrofti will be our model organism for these two infections. They both result in similar disease states, and the parasites are very similar in terms of their genetics as well as their biology. So I feel fairly confident that if I tell you all about Wuchereria bancrofti, you will also learn about Brugia malayai as well. So the infection begins in a rather interesting way. Even though it's vector-borne, when you hear the word vector-borne, you immediately think of a mosquito or a black fly or a tick or a mite perhaps, and they're biting to obtain a blood meal for either their own food or for egg production, as in the case of mosquitoes. And you often think of the infections that they carry as being injected at the site of the bite wound, because that's the damage area, and that's the entry point that most parasites could take advantage of. In this case, you wouldn't be wrong if you thought about the parasite entering the bite wound, but it's sequential. The mosquito doesn't actually inject the infective larvae that it harbors in its biting mouth parts, but rather it actually penetrates the skin to take a blood meal, and in doing so, the larvae are released onto the skin next to the bite wound. When the female mosquito is finished taking her blood meal, which she then uses for egg production, she flies off, and she leaves the larvae of Wuchereria bancrofti right at the site where she obtained her blood. The parasites are perhaps triggered by environmental cues. Perhaps there is some fluid that oozes from the bite wound that stimulates the worm to migrate towards the bite itself rather than just crawl aimlessly along the surface of the skin. We're not sure about those events, but we do know that this is a highly successful parasite which enters the host through that hole that the mosquito just made. It then travels into the cutaneous, then the subcutaneous tissues, and eventually finds its way into the lymphatic drainage system. So this is called lymphatic filariasis for a good reason. These larvae, which are at this point microscopic, find their way into the lymphatics, and wherever they end up in terms of the channels of lymph abutting up against, let's say, lymph nodes. In various parts of the body, there are axillary lymph nodes, inguinal lymph nodes, nuchal lymph nodes around the neck region. These are places where the parasite lodges, because the flow of lymph reaches those areas, and then you've got a tissue to encounter. The parasites set up house right above that. So the efferent vessel coming in is the one in which the adult worms will eventually grow up in. And their food is, of course, the lymph, and laden with nutrients. The parasite then grows to a very long length, centimeters in length, and the parasites live long lives. Now, they also induce a very interesting response in the host, which prevents inflammation. And it prevents the sealing off of these lymphatic vessels as the result. So the worms can have free access to lymph for as long as they remain alive. There are both male and female Wuchereria bancrofti, and these then mate. The females are now impregnated. They produce live offspring, which are referred to as microfilariae. And these microfilariae are able to traverse the organ up against which the worms abut, namely lymph nodes. They can penetrate through the lymph node and out to the afferent end, in which case they can enter the generalized blood supply of the host, and in doing so are now available for being taken up by a new female mosquito on her own search for a blood meal to make eggs, as I mentioned before. So this completes the life cycle, and the female worms can lay many, many hundreds to thousands of microfilariae over the course of a year or 2 years, or even up to 5 years after they infect the host. They can continue to reproduce. The microfilariae are shorter lived. They last at maximum around 6 months before they actually die. So a constant production of microfilariae is necessary in order to maintain this life cycle, because there are seasons for the mosquitoes and all kinds of other interesting phenomena that impact on this infection. Another name for Wuchereria bancrofti is periodic filariasis. And in fact, when they looked to see when the microfilariae are present in the blood of the host, namely humans, there are no reservoir hosts for this infection. Humans are the only host for this one. They couldn't find microfilariae during the daytime in many, many regions throughout the world. In other words, the periodic nature of the microfilariae appearing in the blood occurred at the same time that coincided with the feeding behavior of adult female mosquitoes, namely during the night. So they are night feeders, and as a result, this parasite-host vector relationship has come into synchronicity, so to speak, for the behavior of the host. Sleep at night. This induces the larvae that are collected near the lung fields during the daytime to release and get generalized again into the blood supply. The mosquitoes then feed and have an opportunity for taking up these microfilariae. Each microfilaria is either a male or a female worm, which will later on, of course, through the life cycle, develop to new adults in another host. The worm in the mosquito is a rather interesting life cycle as well. It has some resemblances to trichinella in the fact that the larva, once it's taken up by the adult female mosquito, traverses the gut tract and penetrates into the flight wing muscles, and then embeds itself in a muscle fiber and begins to develop through the life cycle of an L1 and L2 and L3. And once it reaches the L3 stage, it then now penetrates out of the muscle cells of the flight wings and enters the circulation of the mosquito and ends up in the salivary glands and then finally into the proboscis itself. When the mosquito takes a blood meal, as I've said before, the larvae are deposited on the surface of the skin. As she withdraws her mouth parts, the larvae crawl in and resume another infection. It's a very complicated life cycle, but apparently very successful because there are literally hundreds of millions of people infected with these two parasites, Wuchereria bancrofti and Wuchereria Brugia malayai. There's a third member of this family which causes serious disease. It's called Brugia timuri, found in the island of Timor, off the coast of Indonesia. It's a part of the Indonesian archipelagos. And as a result of that infection, there are some very serious consequences with regards to inflammation, which develops after the worms die. The pathology of this infection that results in the enlargement of a limb very much relates to the successful life cycle of the adult females. If the worms die after their lifespan of, let's say, 3 to 5 years, and it could be even longer in some cases, when the worms die, they release their hold on the host's immunological responses that prevent inflammation from developing in that site. And as the result, not only are the worms now dead, so the immune system isn't really playing a role in terms of terminating the life of the worm, but rather what it does is it seals off the lymphatic by this response, both for the Th1 and Th2 responses. They produce a tremendous amount of inflammation. The inflammation then resolves into a large cellular debris, so to speak, which then eventually ends up calcifying, and it blocks the flow of lymph. So that's the basis for the pathology of what's happening in the tissues. Here's just some shots of adult female mosquitoes feeding. And unlike most other infections that we've discussed so far, like malaria, for instance, which only is transmitted by Anopheline mosquitoes, Wuchereria and Brugia can be transmitted both by Culisine and Anopheline mosquitoes, making it more of a generalist host. So as mentioned, the pathology is mostly due to the blockage of lymphatics as a result of the death of the worms. And so, as the adults live in the lymphatic vessels, they secrete inhibitors of cell-host division, which allows the vessel to remain open and allowing for the continuous flow of lymph. The moment the worms achieve their lifespan and begin dying, of course, then that's when all of this cellular reaction occurs. And here's a good example of that shown here. The worms themselves have been calcified as the result of the death of the worm. They didn't die as the result of calcification. They died and then became calcified. So if you want to remember this, you just say, when they die, they calcify. The intense inflammatory response is then directed towards, essentially, a dead worm. And it results in the occluding of the vessels. And you can see in this poor gentleman has had both sets of lymphatic drainages from the long limbs of his legs blocked. As the result, the lymph begins to accumulate in the tissues below the blockage. And it actually serves as a nutrient for smooth muscle cells as well. So if you were to take a section of tissue from any part of either leg and look at it and do a histopathology on it, what you would find, of course, is that most of the tissue is smooth muscle. And that smooth muscle tissue was stimulated to grow as the result of lymph accumulating in below the blockage of these worms. And now Dr. Daniel Griffin is going to give a clinical vignette illustrating the pathogenesis of this infection.
A 60-year-old female farmer in rural India comes in to be seen at a large hospital in southern India. She reports that 4 years ago, she was having fevers, chills, and rigors. And at that time, she was given a diagnosis and treatment, but now comes in with continued swelling of the left leg. After long travel, there's some swelling reported in both legs, but the left is always worse. And on exam, the patient has bilateral pitting edema, but much more edema on the left that is non-pitting. Clinical disease. Now, asymptomatic infection, acute elephantiasis, and tropical pulmonary eosinophilia. So let's go through these one at a time. So we'll start with asymptomatic infection. The majority of residents living in an endemic area do not manifest a strong inflammatory response to their filarial parasite load. They are noted to be asymptomatic even in the presence of circulating microfilaria. Now, some of these so-called asymptomatic patients have been more closely observed, I should say, and there is subtle pathology when they're more closely examined. So there may not be as many people that are completely asymptomatic as we initially suggested. The central event in the pathogenesis of more advanced disease may begin to occur at this early stage in some of these people that we think of as asymptomatic when they start to develop dilation of the lymphatic vessels. Now, the dilation initiates a series of events that results in the chronic clinical manifestations of lymphatic filariasis, including lymphedema and hydrocele. And in some cases, the dilated vessels will rupture and produce chyluria and a chylocele. Now, let's talk a little bit about acute lymphadenitis and filarial fevers. Now, the death of the adult worm causes the next step in the progression of disease by producing this acute inflammatory response that is manifested as acute lymphadenitis. In endemic areas, this occurs frequently during the patient's adolescent years and is manifested by fevers, painful swellings over the lymph nodes. This typically occurs in the inguinal area. Episodes of painful swelling can last a week, and then it can commonly recur. And secondary bacterial infections may also result. Acute filarial lymphangitis also may be exacerbated by these bacterial infections. Some individuals who have traveled to and spent several months in endemic areas can also develop acute lymphadenitis, but the pathogenesis of this process is not completely understood. This phenomenon was actually described in the 1940s among some of the American troops returning from the war in the Pacific Theater. Elephantiasis. Now, this is the clinical presentation that I think is the most characteristic, the one that most of us think about when we're thinking of the lymphatic filariasis. A subset of patients with acute lymphadenitis and filarial fevers will go on to develop lymphedema of the arms, legs, breasts, genitalia. During these inflammatory processes, the skin can become doughy. You get some degree of pitting, but it's sort of a firm pitting. As the inflammatory reaction continues, the area becomes firmer still, and the pitting actually disappears, starting to get a woody consistency. There's substantial spread of the inflammation over the subcutaneous tissue, and we have a loss of the elasticity. Now, characteristically, in contrast to cellulitis, where we have a demarcation, filarial cellulitis shows no demarcation between the affected and healthy skin. The bancroftian filariasis, the legs tend to be more involved in the upper extremities, and the lower portions of the legs are more involved in the upper. The scrotum is frequently affected. You can end up with hydroceles. These can become gigantic, weighing as much as 10 kilograms, and even larger scrotums have been described in rare cases. Tropical pulmonary eosinophilia. Now, this develops in some individuals in some regions with filarial infections. This has been described in southern India, particularly in young adult men, characterized by high levels of serum immunoglobulin E, a nocturnal asthma with interstitial infiltrates on chest radiographs, fatigue, weight loss, and circulating eosinophilia. Left untreated, this can progress to a chronic restrictive lung disease. Now, diethyl carbamazine, DEC, is highly effective in these patients. The pathogenesis of the syndrome is related to a local immune response to the microfilaria in the pulmonary vasculature and results in an eosinophilic infiltrate in the lungs with release of some of the cytotoxic eosinophilic products, so major basic protein and eosinophil cationic protein. And here's a couple pictures, some bilateral elephantiasis. Now, what about diagnosis? Now, microscopy of the blood smear is how one might make a definitive diagnosis, and traditionally this has been depended on. Occasionally, the infection is so heavy that the microfilaria can be observed on a thin blood smear stained with Giemsa. Now, in lighter infections, the methods include filtering blood onto a 0.4 micron pore-sized nuclear pore filter and then staining it. And in the case of very light infection, there's a procedure called the knot test, where a milliliter of blood is preserved with formalin and then concentrated by centrifugation. And then the pellet contains red blood cell ghosts and the microfilaria. This is, I think, gotten to the point where people often refer to a blood smear microscopy exam for microfilaria as a NOT test, even when this specific approach is not used. Now, because of the nocturnal periodicity, it's best to think about that. And in some strains, you're going to want to actually be drawing these either side of midnight based upon the customary hours of sleep. Antigen tests, we can detect circulating Wuchereria bancrofti antigens. This is more sensitive than microscopy and actually can be used during daytime. There's a correlate with worm burden. There's also an ELISA test as well as a immunochromatographic card. And again, this is something that doesn't require the nighttime collection. Serological tests looking for human IgG directed against the worms. These have been developed and are in use clinically in some areas. They're a rapid test that can, they help with detecting exposure, which is not always clearly helpful in endemic areas where there may be widespread exposure. Ultrasound has also provided an important additional modality, and it allows for not only diagnosis, but also efficacy of antifilarial drugs. So ultrasound of the lymphatic vessels of the spermatic cord in infected men has this distinctive sign, the filarial dance sign, where you actually can see these nests of live worms in the lymphatics. And then when you treat, you can actually see by ultrasound that the adult worms are no longer dancing. And here is, we say, the results of a NOT test. So this is microfilaria observed in the blood. And here's the characteristic tip without nuclei and the sheath. Now, what about treatment? I put this up front, just sort of a warning, use with caution. Antiparasitics. It is critical that prior to treatment, co-infection with with a high lower microfilarial count is ruled out due to the risk of serious adverse events. Now, this is going to come up a couple times when we treat things. You always want to know, is there something else going on? Because you may feel like your treatment is innocuous in this context, but a second infection may cause you problems. So diethyl carbamazine can be given. Doxycycline can be given. Ivermectin and albendazole are being used as parts of mass drug programs. Now, surgery. Hydrocele drainage without corrective surgery is going to really just end up with reaccumulation. So you actually, if you're going to address hydroceles, you need to address them properly with proper surgical technique, not just with drainage. Now, the surgical techniques have really been developed that do a great job of alleviating the hydroceles, greatly improving the morbidity. And unfortunately, sometimes when you treat, you can precipitate the development of these scrotal hydroceles. So a lot of communities, when they've introduced filarial-free drug, mass drug programs, there's been an agreement that should this trigger hydroceles, that surgical teams will come in and address this. And important to remember complementary care. You want to be treating the lymphedema because this is going to be a chronic issue. And you also want to be very careful with treatment of wounds and secondary bacterial infections. Now, what about our patient? Our patient was initially treated when they presented with active filariasis with 21 days of DEC. Repeated evaluations did not detect microfilaria in the blood on night draws. And at this point, the patient is continuing with treatment for lymphedema and chronic preventative skincare.
Preventing or controlling of lymphatic filariasis very much depends upon the presence or absence of community health services. It can also depend on mosquito control programs, which are aimed at controlling, let's say, malaria. But in this case, because culicine mosquitoes can also transmit the infection, you would have to direct those efforts to a wider range of mosquito biologies. And very often, they only have so much resource. And if you had to make a choice between controlling the mosquito that transmits malaria or transmitting the ones that transmit filariasis, you would probably pick the malaria because of the more serious nature of the infection, and particularly in children. Community-based ivermectin treatment for school kids and for adults that can be identified and treated as a group is part of a larger program in which anti-helminthic drug is used. So there's a cocktail that's now been developed using mebendazole, which you will recall is a good treatment for most of the helminths, and ivermectin, and in some cases diethylcarbamazine as well. But because the diethylcarbamazine was used indiscriminately in communities where loa loa was also found, it was later on discovered that the loa loa is a contraindication for using diethylcarbamazine. If you want to learn more about lymphatic filariasis, and there's a tremendous amount of data with regards to its epidemiology and its molecular biology as well, because the entire genome has been sequenced. There are many, many, many references that could be recommended, but in this case, here's an article that says, can we eliminate filariasis by the year 2020? Well, they better hurry because there's only 3 more years left. There's another reflection on the use of ivermectin and how it was discovered. And this is the Nobel Prize lecture given by Dr. William Campbell, and I highly recommend it. It's a very interesting tour of drug discovery and the use of that drug to control filarial infections in general. And finally, we have an episode, number 25, on TWIP, which you can access at microbe.tv/TWIP for your listening pleasure. And so next time, we're going to continue our discussion of filarial infections. And in this case, we're going to discuss river blindness caused by Onchocerca volvulus. Thanks for listening.